Hi, this is Zheng Chen. I'm from Math Department of UMassD ACCOMPLISH. In this video, I'm going to talk about the numerical integration module for UMassD ACCOMPLISH program. So the overall goal of this module is like, we want the student to learn how to do numerical integration, which means using numerical methods to approximate integration of a given function. And the outcome of this module is going to be a GUI MATLAB graphical user interface MATLAB program. So here is how the GUI looks like at the end. So it's going to be an interface that the user can put in the expression of the function, the range for integration, and choose the method for numerical integration. And once click the calculation, the result will show here. And also some plots for certain methods will be showing up here. So that's the outcome, the overall goal of this module. So about this user interface, the framework of this GUI will be provided. So the students don't have to code up that part. But the key part here is we want the student to learn about the numerical methods, and they need to understand them correctly and also be able to finish the codes for those methods, only the parts for those methods. So for those parts, it will be leave blank. And at the meantime, the full version will be provided by to the advisor. So the advisor will know how it works, what is the correct thing. But the students need to figure out how to fill in blanks. So again, the student's mission is to study the different numerical integration methods and then finish the routine for each method. So that routine, that missing part is under the function calculate push button callback in the main file. So more details will be talked about later on in this presentation. This is the screenshot of that function. And you are going to look for this line, and you will see the missing part inside this function for each method. It's well commented. And also we will show screenshots later once we talk about each method. So there are many numerical methods for integration. And in this GUI, we're going to cover the following methods: the midpoint method, trapezoidal rule method, Simpson's rule method, Simpson's 3/8 rule, and also the composition numerical integration methods with this method. And the last one, we will demonstrate Monte Carlo integration. And this is well used in application, but it's very costly. So the code of this part is given. So the student don't have to code this up. It's just for fun for the students. And also this GUI has potential to be extended to include other methods if the student would like to do that. So we have this flexibility there. So here is the table of the contents for this presentation. First, I talk about the goal, and then I will talk about why we want to do this. What is the motivation? And then we will talk about some basic ideas of numerical integration methods, how it works. And then we will first talk about some simple ones like this 4. And then I will show you what is concept, what is the idea of the composite numerical methods with these simple rules. And here we only list the 2 examples, but the same idea can be applied to the others. And last, we'll briefly introduce what is the Monte Carlo integration. So that's the overall, that's the table of contents. Okay, we have covered the goal. Now let's see what is the motivation. So for the motivation, I'd like to use this application, this example, to demonstrate motivation. So think about this. If you're considering constructing a house and you're looking for materials to cover the roof, and the roof is definitely not a plain sheet like this, right? You need to curve it a little bit like this. So suppose you want to press a flat sheet of aluminum into this wave shape, this sine wave shape. Then we know how long we're going to cover, what is the length of the roof. But the question is, how much material you're going to need, you're going to book, you're going to buy, right? So that's the question. So you know the length of the shaped version, and you want to see what is the original length so that you can budget, you can buy it, right? So that's application. And but we need to form this into a function, and then we can use the concept of integration to figure out this question. So suppose we are going to cover a 4 feet long roof, and we want to see what is the curve length, right? So that's the question. And from calculus, probably you still remember how to calculate this curve length. And that is going to be integrating the curvature throughout this domain from here to here, which is from 0 to 4 feet, or with a 48 inch, right? So we just need to calculate what is the curve length, curvature. And from calculus, we know the curvature is just square root of 1 plus the function's derivative squared, right? So this is a sine function. So we have sine function here. We take a derivative, we take the square, we sum it up with 1, and then take the square root. This is the curvature at the location X. And then if we integrate this curvature from 0 to 48, then we get the overall length of the original material for this 4 feet long sine wave shape, right? So that's how we calculate that. So after simple calculation, you find out you need to get the value of this integration. Okay, now we come to the motivation. If this one is a simple function, you can figure out what is the antiderivative, then that's trivial, right? You can just find the antiderivative and then evaluate at the two ends. That's how we do that in calculus. But for most questions, for a lot of applications, this function doesn't have antiderivative, or it's going to be very complicated to evaluate. For those cases, we don't want to use the antiderivative and evaluate that, right? So the motivation is this. And what if we can use computer to approximate this out? And we can have something programmed very well. You just need to tell what is the integrand, what is the function, and where you want to integrate this function from, and where you want to integrate function to, right? If you can give only these 3 inputs, and the computer can tell you a good enough results, then you can just use that results. And the good thing here is the code, you can just do that once, and then you can just put in different integrand function, different range, then that code will just run for the results, right? So it's like one effort and you get results for whatever function you want. So that's the motivation. We do this integration numerically, which means we use computer, we code up things to use computer to calculate out a good enough approximation. So that's the motivation. Okay, now the question is, what does numerical integration looks like, right? So let's look at some basic things about that. The numerical integration, as I mentioned, is going to evaluate some definite integration of an integral of a function for which one it doesn't have explicit antiderivative, or the antiderivative is very easy, is not easy to obtain or very hard to compute. For example, this, you integrate cosine x squared, or you integrate e to the power negative x squared, not just x, right? So for those things, the antiderivative is not easy to get. Okay, so then how the numerical integration looks like. There's another name. We also call this thing numerical quadrature. The reason is that we usually approximate something like this, the integration of some function, f. It's like just abstract expression for that, from a to b, two numbers, right? From number a to number b. Then this actually can be approximated by you're looking for the function's value at certain points, xi's, those are the chosen points, and then you give them a proper weights for each point. For each xi, you assign a number, ai, we call it a weight here. And if you have this multiplied together and sum up over all the selected points, then that will give you a approximation for the numerical, for the integration. So this is also called numerical quadrature. And all the selected points, xi's, are called nodes, and the associated weights, ai's, the number here, are called weights. So usually for a given, for assigned numerical integration methods, the location xi's, the ai's, the weights are determined. So once you point out you want to use which method, you know what are the points and the weights. And different points and weights, different nodes and the weights will give you different numerical methods. So let's look at some basic ones. The very first one is called middle point rule. So what is middle point rule? If you remember from calculus, the integration of function is actually you're calculating the area below the function, below the curve. By the area, we mean the signed area, right? It can be positive, can be negative. It depends on whether it's above the x-axis or below the x-axis. So we sum up this signed area, then that's meaning of integration. But the middle point rule here is we want to approximate that area of the region below the curve by using a rectangle. And that rectangle is with the same height, the height of the middle points, I mean the function's value at the middle point. So for example, if you want to approximate this integration of fx from a to b, then you just need to find out what is the middle point. The middle point is the points in between these two endpoints, right? The lower limits and upper limits, and that is the average of those two, a plus b over 2. And then if you evaluate function f, the integrand at this point, then you get the height of the rectangle. And then you times that with h, which is the width. And for this case, it's b minus a. Then this is the area for that rectangle. And it is approximation for the area under the curve of function y equals to fx, right? So this is a way to approximate the integration. It's the most simple one. You cannot expect this to be very accurate if the function f varies tremendously, but still this is the first one we can play with. So this is the formula, and this is how you understand that. And this is the approximation, the thing you want to code up and return this value as approximation provided by midpoint rule, right? So in our GUI, in the M file, under that function, the call button function, what is that? This push button function, calculate the push button callback function. Right under this, you will find out the part about midpoint rule. So it looks like this. And because in the GUI, the user can input which method you're using. So if you in the option, if you choose midpoint rule, then it will read as 3 for this value, for this variable method. And then it will go to this part to finish calculating the result, the integral, I mean. So here you need to finish the sentence, the line here, the code here, so that the integral here, you will assign this to the integral, right? So that's what the code here is functioning for. And the student need to get this part done, fill in the blank here. So first thing, you need to find out what is h, and next you need to find out what is this average, and then evaluate the function of this average, and then get a product and assign that to integral, right? This is just how we do that by looking at this. So because this is the first one, I will explain, I will tell you what to do, but for the following one, I will leave them blank on purpose so the student can work them out by themselves. So that's the middle point. And you're going to fill in the blank here so that the integral equals to this thing, right? Equals to this formula. So that's for middle point rule. And the next one is called trapezoidal rule. So this is like advanced version compared to the middle point. And what it's using is using a trapezoid, which is formed by these 4 points. So the points A on the x-axis, the points B on the x-axis, and also the function's value at these 2 points, when you evaluate at these 2 points. So these 4 points will form a trapezoid, and the area of that one will approximate the area below this curve, which is the integral, the exact integral, right? So that's the trapezoidal rule. And the formula for that is just the area of a trapezoid, right? So the width, which h here is b minus a, the width times fa, the length here, plus fb, the length here, and then divided by 2. So that's the formula for the approximation by trapezoidal rule. And in the GUI, the students need to code up how to assign this value to integral here. We need to fill in that blank here by doing this, by assigning integral with this value, with this approximation. So that's trapezoidal rule. And for Simpson's rule, now we are using more and more points, right? Middle points, we just use the middle point, 1 point. Trapezoidal rule, we use 2 points, the 2 endpoints, lower limits, upper limits, right? And for the Simpson's rule, we are going to using 3 points. So the 2 endpoints and the 1 middle points. And then you are going to form a quadratic function, and that quadratic function, the area under that quadratic function will approximate the area under the real curve. So the result provided by this area is called Simpson's rule. And the formula actually looks like this. So x0 is the A, x1 is the middle point, x2 is the B. And h here is the distance between 2 neighboring points. So h here is x1 minus x0 or x2 minus x1. They're equally spaced, so they're the same, right? So this is the formula. So for the Simpson's rule, the student need to fill in the blank for these parts. You look for the comments with Simpsons or this line if method equals to 5. And students need to code up here to assign the integral with this approximation value provided by this formula. So that's for Simpson's rule. The next one is the Simpson's 3/8 rule. So this actually 4 points. X0 is the left one, the lower limit A. X3 is the upper limit B, and X1, X3, X1, X2 are the 1/3 and 2/3 points. So the H here is the distance between the neighboring points, which is X1 minus X0 or X2 minus X1 or X3 minus X2. All 3 of them the same, right? So this is the formula for Simpson's 3/8 rule, and students need to finish the part here and they will look for the common Simpson 3A's and replace these common parts by assigning integral with this value. So that's for Simpson 3A's rule. And now we have introduced all four simple basic integration rules. Now let's look at the composite version. So what is the composite numerical integration? The idea here is that if your function, the integrand, is very complicated, it varies a lot, it will not be possible to approximate the integration by just 1, 2, 3, or 4 simple nodes, right? It's not possible. So what we can do is we can divide the whole integration interval into sub-intervals. And then for each sub-interval, we apply the simple one. So for example, the composite middle point rule is like we divide it into like n sub-intervals, and for each one, we choose the middle point. So basically you approximate the integration of this function over the small interval with the middle point rule, and also for the next sub-interval, and for each sub-interval, and then sum them up, right? This is the composite middle point rule. So basically break the problem into small sub-intervals and do the basic rules on each one and then sum them up. So for the composite middle point rule, the formula is going to look like this. You just need to figure out what is the where the middle point for each sub-interval is, and that's actually given here. So for xj, which is the middle point of j sub-interval, it's going to be a plus j plus a half h, right? So that's the location for xj. You evaluate the function f, the integrand function, on that location, sum them up, and then times the length for each sub-interval, right? Or the other way to think about that is you have h times this fxj and then sum them up, right? So that's the composite middle point rule. And h here is the length of this sub-interval. So it's actually equals to 1/n of the whole length, b minus a, right? So it's this. So how do, what should we do in the GUI? You just need to look for the location, the parts for composite middle point rule. And then this line here is actually reading from interface. The user will, once the user choose composite middle point rule, there will show up a location. So students, so the user can put in how many sub-intervals they want to use. So this line will read that number and assign the number to variable n. And then later you need to use this n to code up this. That n here is this little n here, right? So you need to remove these comments by some code, several lines of codes to get this integral. And also here, you'll probably want to use the for loop to get the summation done. So that's for composite middle point rule. And next one is the composite trapezoidal rule. So same idea, you break that, you break the whole interval into n sub-intervals, and for each one you use trapezoidal rule. So you basically use a trapezoid to replace, to approximate the area under the curve on this sub-interval. And once you find the area here, you sum up all the areas of the trapezoid formed by the sub-intervals, right? So the formula for that is actually this. You basically sum up the function's value at all ends for each sub-interval. And because, for example, at this point, this length will be counted 2 times. Once comes from the area of the left sub-interval, the left trapezoid, and the other one, the second one, comes from the when you're calculating the area of the right trapezoid, right? So that's why for all middle points, interior points, you will have double counts here, right? But for A and B, they're only counted once because they're only form one trapezoid. And H here is the length of this subinterval. And that's, again, B minus A over N. So this is a formula for composite trapezoid. And the students need to finish the part using the help of for loop, or if the student's good at vector language in MATLAB, they can just use some summation language. But the basic technique is using for loop for beginners. So the students need to replace its comments by code up and assign integral with this approximation. So that's the composite trapezoid rule. And that's the last part the student need to work on in this GUI. And we also include Monte Carlo integration in the GUI. This is just for fun. The student doesn't need to code it up. The codes are provided. So what Monte Carlo integration? Monte Carlo integration is like you are sending random points and you evaluate the function at those random points. And then you take the average. The way you take average depends on how you choose random points, right? So basically you just throw out random points and then evaluate this function at those random points. So this is how it looks like when you use this GUI with Monte Carlo method. And for this complete function, it's going to look like this. And the blue area at the area with positive signs, and the red one at the area with red signs. And in another another video, I'm going to demonstrate the complete product of this GUI MATLAB app code, and that is what expected once the student finish putting in all the missing codes. So that's the end of this demonstration. This demonstration of numerical integration module for UMassD ACCOMPLISH program. Thank you.